Welcome to this video on compound probability. Compound probability involves compound events, which is a combination of two or more events. Using the word and or the word or. All right, so let's talk about the different types of compound events. The first type of event is an OR event, which is going to have unions, and we're going to add in this particular case. So there are two different types of OR events or union events. The first one is mutually exclusive, and that is events with no common outcome. And then overlapping events, of course, are events that do have a common outcome. All right, so the formula for a mutually exclusive event, so we're finding the union of the probability of A and B. We're just going to add the probability of A plus the probability of B. And for overlapping, it's still a union. We're still going to add. But because they overlap, I'm going to subtract where they overlap. I'm going to subtract the intersection, which we will talk about how to do that when we get to an example. So let's talk about examples of mutually exclusive and overlapping events. All right, so a mutually exclusive event being a 9th grader or a 10th grader. Those are mutually exclusive because you can't be both. You have to be one or the other. They cannot happen at the same time. An overlapping event would be being a 9th grader or being in the band. Those can happen at the same time. You can be in 9th grade and also be in the band. All right, the other type of event is an AND event. So if you need some more time to finish writing these notes, pause the video now. Okay, so AND events are intersections, and we're going to be multiplying in these events. So the first type is an independent event, and that is events that don't affect each other. They are independent of one another. And then dependent would be events that do affect each other. Okay, the formula for independent, so these are intersections. Probability of the intersection of A and B is the probability of A times the probability of B. So we're going to multiply them together. And then for dependent, it's the probability of A times the probability of B given A. And we will apply those formulas when we get to examples. So examples of independent events would be like flipping a coin, or rolling a die. If you flip a coin and you get tails, that outcome doesn't affect the next time you flip a coin. It's still a 50-50 chance every single time you flip a coin. They are independent events. They don't affect each other. An example of a dependent event would be drawing a card from a deck of cards without replacing it. So if you have a deck of 52 cards and you draw one, but you don't put it back, the next time you draw a card, you have 51, so you have changed the next probability. So they are dependent upon one another. All right, let's go over some examples. So these examples will involve a deck of cards. So if you want to print a picture of a deck of cards from online, that might help you if you're not familiar with a 52 set of deck of cards. All right, so number 1, you randomly choose a card from a standard deck of 52 playing cards. Find the probability that you choose a queen or an ace. Okay, so first of all, when you're dealing with these problems, you want to determine, is this an and event or an or event? So we're looking in the problem, and you're looking for the word to be in between the two events. So queen and ace are my two events, and the word between those is the word or. So this is an or event. So let's scroll back up. So or means we're going to add. And we have to determine, is it mutually exclusive or overlapping? So let's go back. All right, so let's find the probability of a queen first. So think about a deck of cards. There are 4 queens out of 52 total. All right, or means to add, so plus. And then let's look at the ace. There are 4 aces out of 52. Now let's determine if this event is mutually exclusive or overlapping. Can you have a card that's both a queen and an ace at the same time? Your answer should be no. You can't have a card that's a queen and an ace, so these are not overlapping. They are mutually exclusive, so I don't need to worry about subtracting anything. I just add these together, which is 8 out of 52. And then you want to reduce that. That would reduce to 2/13. And if you want to change it to a decimal, about 0.15 or 15%. So all 3 of these are correct, just different forms. All right, next, find the probability that you choose a king or a club. So this is another or event we're going to be adding. So let's do kings first. There's 4 kings in a standard deck of cards. And then clubs. So there are 13 clubs, and there's 13 of each suit. Clubs, spades, hearts, diamonds. So there's 13. Now let's determine, are these mutually exclusive or do they overlap? Can a card be both a king and a club at the same time? Your answer should have been yes. There is one card that is a king and a club at the same time, the king of clubs. So we need to subtract that one card, because otherwise we're counting it twice. We're counting it as a king and we're also counting it as a club, but it's just one card. We don't want to count it twice. So I'm going to subtract it. So let's see, 4 plus 13 is 17, minus 1 is 16. And then reduce that. That would be 4/13 or 0.31 or 31%. All right, next, find the probability that you choose a card with an even number or a heart. Okay, so if you have your picture of a standard deck of cards, see if you can count the even numbered cards. Don't worry about jacks, kings, queens, just the numbers that are even. All right, you should have gotten 20. There's 20 even numbered cards. This is an or event, so we're going to add. And then hearts, there are 13 of each suit, so there's 13 hearts. Now, let's think, are there cards that are both? Is this an overlapping event? Can a card be even and a heart? So look at your picture. Count how many are both. All right, you should have counted 5 that are both. 2, 4, 6, 8, and 10 of hearts. Those are both even and hearts, so we're going to subtract those 5 because otherwise we're counting them twice, but it's just one card each. All right, so let's add these together. 20 plus 13 minus 5 is 28 out of 52. Let's simplify that. That would be 7 out of 13, or 0.54, or about 54%. All right, number 4, find the probability that you choose a heart or a spade. So there's 13 hearts. This is an OR event, so we're adding. There's 13 spades. All right, let's see if this overlaps. Are there any cards that are both hearts and spades? All right, you should have said no. These are mutually exclusive events, so we don't need to subtract anything. We just need to add those together. So 26 out of 52. And then that reduces to 1/2, or 0.5, or 50%. And if you think logically about that problem, if you're choosing a heart or a spade, well, that's half the deck. All right, next one, number 5. A coin is tossed and a 6-sided die is rolled. Okay, so the word in between these two events is and, so we're going to be multiplying here. What is the probability that the coin shows heads and the die shows a 5? So let's do the coin first. So the probability that a coin shows heads, that's 1/2, times a die showing a 5. Well, think about how many 5s there are. There's only one 5 out of 6 possible numbers. And let's go back up. So this is an and event. We're multiplying here. We need to think, is this independent or dependent? And if you're talking about coins or dice, those are always independent of one another. So all we need to do is multiply them together, and that will give us our probability. All right, so 1/2 times 1/6, that's 1/12. As a decimal, that's 0.08, or 8%. Number 6, what is the probability that a coin shows tails and the die shows an odd number? So this is another and problem. So coin shows tails, that's 1/2, times, because it's an and problem, the die shows an odd number. Okay, so think about how many odd numbers there are on a die. There are 3 out of 6. So 1/2 times 3 out of 6, that would be 3 out of 12, or 1/4, which is 0.25, or 25%. All right, number 7, an aquarium contains 6 male goldfish and 4 female goldfish. You randomly choose one fish from the tank without replacement. That means you take the fish out, but you don't put it back in. When you select another fish from the tank, what is the probability that both fish are male? Okay, so first of all, let's determine if this is an and problem or an or problem. All right, so we choose one from the tank, then we choose another. What is the probability that both are male? So we really don't have either word here, but I'm going to give you a little tip. If you see the word both, that tells you it's an and problem. So you may want to go back up to your notes here and add the word both. Both, because we want this one and this one to happen. Okay, so while we're here, because it says without replacement, this is a dependent event because we have changed the probability by not putting the fish back. So dependent. All right, so let's find the probability of the first fish being male. So we have 6 male goldfish, and then there's 10 total. So 6 out of 10 is the first probability. I'm multiplying here because it's an and problem or a both problem. Now, we took one fish out, but we did not put it back in. We put it in another fish tank so it didn't die. The next time we choose a fish, because we took one male out, now there are only 5 males left. And we took one out, so there's only 9 fish total. So the probability has changed for the second fraction. All right, so let's see what we get here. That would be 30 out of 90, or 1/3, 0.33 or 33%. All right, number 8, use the following information to determine if the events are independent. Okay, so if the events are independent, I should just be able to multiply them together and get the intersection. So I should just be able to multiply 0.5 times 0.7 because nothing has changed. These are independent of one another, so one is not changing the other. They should just give me the intersection. So 0.5 times 0.7 gives me 0.35, so that would be yes, they are independent. All right, and then the next one, 0.3 times 0.2. That gives me 0.06. That's different than the intersection, so that must mean that one is changing the other. It's dependent, so that would be a no. All right, a few more examples here. The table below shows the results of a survey of an 11th grade and 12th grade students at Brookdale High School. And they were asked if they had a job last summer. So this is a two-way frequency table. I'm going to find my totals first. So I'm just going to add vertically and horizontally. So you go ahead and fill it in on your notes too. All right, so we are going to use the table to find unions and intersections now. So number 10, we want to find the intersection of J and T. So on a table, it's really easy to find the intersection. You just literally find where the two intersect. So J and T, they intersect here, 30 out of the total 80. So when you want to find our intersection, you just find where the two intersect. And then of course we can reduce that to 3/8, and then you can change it to a decimal percent if you would like. Now for a union, remember we add the probability of both and then we subtract if they overlap. So let's find the probability of N, which is not having a job. So there are 32 students out of 80 that don't have a job. And then let's find the probability of T being a 12th grader. Oops. There are 40 12th graders out of 80. And then we want to subtract if they overlap. And in a two-way frequency table, there are always going to be overlaps. So T and N overlap here. So I need to subtract these 10 students because otherwise I'm counting them twice. They're only one person. I don't want to count them twice. I just want to count them once. All right, so let's go ahead and add that up. 32 plus 40 minus 10 gives me 62 out of 80, or 31 out of 40. All right, pause the video now and try 12 by yourself. Okay, so let's see how you did. The probability of no job is 32 out of 80. The probability of being an 11th grader is 40 out of 80. They intersect at 22 out of 80. So that gives me 50 out of 80, or 5/8. All right, last example, let's go ahead and add across and add down. An optional workshop to improve players' basketball skills was held for varsity players. 1 month after the workshop, data was collected about the players who did and did not attend to see if any had improved their skills. So these are, again, unions and intersections, but they're just in words instead of symbols. So find the probability that a player chosen at random attended the workshop and, I bet that's going to be important, showed improvement. So this is an and problem, which means it is an intersection. So normally for intersections we multiply. However, on a two-way frequency table we can just find where they intersect. So attended the workshop and showed improvement. That would be here at 44 out of, there's 100 total. And since this is out of 100, let's just write these as percents. That's easy, 44%. All right, 14. Find the probability that a player chosen at random did not attend the workshop and showed improvement. So they did not attend, but they showed improvement. 6 out of 100, or 6%. And then 15, find the probability that a player chosen at random attended the workshop or showed improvement. So or means add and then subtract. So they attended, let's see, that would be 62 out of 100. They showed improvement, so 50 out of 100. But let's subtract where they overlap. That would be 44 out of 100 because we don't want to count those students twice. So let's see what that gives us. 68 out of 100, or 68%. All right, you can stop the video now and complete the practice and check it with your teacher.